The first thing you hear is not the wind, it is the air system keeping you alive. Outside this wall, the atmosphere is too thin to breathe. The temperature can kill you. Radiation reaches the ground with almost nothing to stop it, and Earth is so far away that a simple reply may take nearly an hour. Yet somewhere above you, a city is waking up. The lift climbs through 6 meters of Martian soil. Its doors open onto a landscape that looks nothing like the Mars of science fiction. There is no giant glass dome, no silver skyline, just low red ridges, frost-covered pipes, landing pads in the distance, and machines moving through the dust. Most of the city is underneath your feet. This is what Elon Musk says SpaceX ultimately wants to build, a self-sustaining civilization on Mars, potentially home to more than 1 million people. But 1 million people cannot live on a promise. They need air, water, food, power, medicine, and factories. And if the next fleet from Earth never arrives, the city must not die. So, what would Musk's first city on Mars actually look like? And which part of it is real today? The Mars plan begins with a machine taller than the Statue of Liberty, Starship, and its super-heavy booster. SpaceX is developing the system to be fully and rapidly reusable. That word, reusable, is the entire economic argument. A disposable rocket is like flying an airliner once and throwing it away. A city on another planet needs the same vehicle to fly again and again, carrying people, excavators, reactors, pressure vessels, and every spare part no one remembered on the first flight. SpaceX says establishing a self-sufficient city may require upward of 1 million people and millions of tons of cargo. The scale is difficult to picture. A few ships can create an outpost. A city requires a transport system.
Progress is measured by the timeline to establishing a self-sustaining civilization on Mars. That's how we're gauging our progress here at Starbase. So with each launch,
and that system does not exist yet. Starship has made major test flight progress, but rapid reuse, orbital refueling, and safe human transport to Mars are still engineering goals. Musk's dates are targets, not confirmed mission schedules.
That distinction matters. We are not looking at a city SpaceX has already designed room by room. We are taking its declared objective and asking what the laws of Mars would force that city to become. The first decision is not the shape of a building. It is a point on a map. If you could place the first settlement anywhere on Mars, the equator might look tempting. More sunlight, warmer days, easier solar power. But a city cannot import all of its water from Earth. NASA's orbital surveys have identified broad regions in the northern mid-latitudes where water ice may lie just below the surface. Arcadia Planitia is one of the strongest candidates. It sits in a compromise zone, far enough north to reach shallow ice, but not so close to the pole that cold and darkness dominate the year.
Different locations. The lead candidate right now is the Arcadia region. So and Mars has a lot of real estate, but when you combine all of the factors and say, okay, we can't be too close.
Lower terrain also gives an arriving spacecraft a little more atmosphere to use during descent. On Mars, even geography becomes part of the braking system.
Arcadia Planitia is not an announced SpaceX city site. It is a scientifically motivated example. Before people arrive, radar, drills, and robotic scouts would still need to confirm how much ice is present, how clean it is, and whether the ground can support repeated landings and heavy construction.
The first map of the city would therefore be a map of invisible things: ice under the soil, stable rock, safe landing corridors, and slopes shallow enough for machines. Then the cargo starts arriving. Imagine the first fleet reaches Mars without a single passenger. One ship carries power systems, another carries excavators and autonomous haulers, a third brings communications, pressure modules, and replacement parts. A fourth is almost entirely a chemical plant. Robots deploy the first electrical grid, inspect the ice, and bury habitats under piles of regolith. They also prepare something less glamorous but essential: a proper landing zone. A vehicle as powerful as Starship descending near unprotected equipment can turn loose rock into high-speed debris. The first settlement cannot grow if every new arrival sandblasts the last one. So the city begins as separated islands: a landing complex, a habitat zone, a power zone, and an industrial zone, connected by pressurized rovers and buried cables. Only after the system survives a Martian season without human repair does the first crew commit to the journey. And when they step outside, the most valuable resource around them is not gold, iron, or land. It is dirty ice. Water ice can become drinking water. Split it, and it becomes oxygen and hydrogen. Combine that hydrogen with carbon dioxide from the atmosphere, and it can become methane. Methane and oxygen are the propellants Starship is designed to use. In other words, the same buried deposit could support people, crops, and the fuel supply needed to leave. NASA has already demonstrated one small part of this chain: the MOXIE experiment aboard Perseverance pulled carbon dioxide from the Martian atmosphere and produced oxygen.
MOXIE made 122 grams of oxygen over its mission. At its best, it produced about 12 grams per hour at very high purity. That is a successful demonstration, but a person consumes roughly that amount in tens of minutes. A city needs industrial plants, backup plants, and storage measured in tons.
And breathing is not even the biggest oxygen problem. Rockets burn far more oxygen than people inhale. A return vehicle needs an enormous stockpile waiting before anyone trusts it as a way home. This is why the first true landmark on Mars may not be a monument. It may be a row of insulated tanks beside a plant that runs day and night, slowly turning atmosphere and ice into survival. Every pipe has a twin. Every pump has a spare. Every tank is divided so that one leak cannot empty the settlement. Because on Mars, redundancy is not inefficiency, it is architecture. Science fiction usually places a Martian city under glass. Real physics pushes it under dirt. Mars has no global magnetic shield like Earth's, and its thin atmosphere offers little protection from cosmic radiation. A transparent dome would also hold back a pressure difference across a vast surface while being struck by dust, temperature cycles, and micrometeorites. The safer material is already everywhere: rock and regolith. Early habitats could be rigid modules covered by several meters of soil. Water tanks can line occupied spaces and add shielding. Later construction may tunnel into hillsides or investigate lava tubes if their geology and biological cleanliness allow it. From the surface, a district may look like a low ridge with airlocks. Inside, it opens into workshops, clinics, kitchens, classrooms, and narrow public spaces built around one rule: no wall is allowed to be just decoration.
We do not yet know the lifetime health effects of living permanently in 38% of Earth's gravity. We also do not know whether pregnancy and childhood development would be safe. A city can shield radiation. It cannot simply engineer away every biological unknown.
That uncertainty shapes daily life. Exercise is infrastructure. Medical imaging is infrastructure. Centrifuges may become as important as parks, and all of it depends on electricity. On a clear day, Mars offers sunlight across enormous empty plains. Solar arrays are easy to expand, contain no moving fuel, and can be deployed by machines. Then the dust arrives. Martian dust can coat panels, and regional storms can weaken sunlight for weeks. NASA therefore treats surface fission as a serious option for reliable power. The credible city uses both. Solar fields provide abundant energy when conditions are good. Batteries and other storage stabilize short interruptions. Compact fission units provide firm power through night, winter, and dust. The grid is divided into islands. A fault in the farm must not stop the oxygen plant. A cable failure in one district must not freeze the water system in another. Waste heat is captured for habitats, pipes, and industrial processes. Power is not a line item in the city budget. It is the heartbeat behind every breath. And after air and heat, the hardest requirement may be the one that looks easiest in concept art: food. The first crews eat mostly packaged food from Earth. It is predictable, compact, and already tested for long missions. Fresh crops begin as supplements: lettuce, herbs, dwarf tomatoes, beans, and other plants selected for nutrition, reliability, and efficient use of light. Indoor farms recycle water, recover humidity, and turn carbon dioxide into biomass. They also give people something alive to care for in a world where nothing green grows outside. But a wall of lettuce is not a food system. A settlement needs calories, protein, fats, micronutrients, seed stocks, pollination, disease control, and a plan for crop failure. Every kilogram of fertilizer must either be imported or recovered from local materials and waste. NASA's CHAPIA missions simulate pieces of this problem on Earth. Small crews living for about a year inside a 3D printed Mars habitat, facing constrained resources, isolation, and delayed communications.
Those experiments do not prove a closed Martian farm. They reveal where people and systems fail before the consequences become fatal.
At city scale, farms become bright multi-level factories. Their windows face inward, not toward the landscape. Food is engineered around reliability long before it is engineered around choice. That may sound bleak, but the strangest part of life on Mars is not the menu, it is the distance. A Martian day is only about 39 minutes longer than a day on Earth. Human schedules can adapt. Human conversation cannot defeat the speed of light. Depending on where the planets are, a message may take roughly 4 to 24 minutes to cross the gap one way. A question and its answer may need 8 to 48 minutes. There are no live family calls in the ordinary sense. You record a message, send it, continue your day, and wait. The city needs local doctors because Earth cannot guide an emergency in real time. It needs local law because a government millions of kilometers away cannot approve every decision. It needs schools, entertainment, data centers, and people authorized to repair systems without asking permission. Dust changes behavior too. Residents move through suit ports and cleaning locks so the abrasive, chemically reactive soil does not spread through living spaces. Outside work is planned like a dive. Inside, maintenance never truly stops, and the local economy begins with an uncomfortable fact. Almost every useful object initially costs a trip through interplanetary space. The only way out is industry. At 20 residents, the settlement is a mission. At 1,000, it is a town that still depends on Earth. At 100,000, it needs mines, refineries, foundries, chemical plants, and factories capable of reproducing the machines that built them. At 1 million, the challenge is no longer bed space. It is supply chains.
This is just guesses, obviously, but we need to get about a million tons, is my guess, to the surface of Mars to make a civilization on Mars self-sustaining. Again, to that critical point where
The city must make pressure seals, bearings, glass, wiring, structural metals, and eventually advanced electronics. It needs medicines, machine tools, and laboratories that can diagnose a failure nobody predicted. A single missing component cannot be allowed to disable the factory that makes all the others. This is the real meaning of self-sustaining. Not that the city never trades with Earth, but that a missed launch window does not become an extinction event. Picture the growth across decades. New fleets arrive when Earth and Mars align. Ships land far from the homes, robots unload equipment, tunnels extend. Old pressure modules become workshops. Water, oxygen, and power production grow ahead of population because on Mars spare capacity is time. The skyline stays low. The civilization grows downward and outward. Even the perfect city plan is trapped behind problems that no rendering can solve. Starship must launch repeatedly, refuel in orbit, survive the months-long transfer, land heavy cargo on Mars, and eventually leave again. Every step must become routine enough to risk families, not just test pilots. Human bodies must tolerate radiation, isolation, and partial gravity for years. No one has spent a lifetime at 38% gravity. Then comes politics. Who owns the industrial system that controls the air? What rights does a worker have when leaving a job may also mean losing a habitat? Which laws apply when Earth cannot enforce them quickly? And there is a scientific paradox. Mars may preserve evidence of ancient life. A human settlement brings Earth organisms in its air, water, waste, and machinery. The larger the city becomes, the harder it is to protect the very evidence that made Mars scientifically valuable.
None of these questions proves that a settlement is impossible. They do show why a transport vehicle, however impressive, is not the same thing as a civilization.
Return to the lift where our journey began. The doors close on the red horizon and descend into the city, past the radiation shielding, past water tanks and power cables, past farms, workshops, and a school preparing children for a planet their grandparents only saw through telescopes. The spectacular machines are all on the surface. The civilization is below. Musk's million-person vision is physically imaginable because many of its individual pieces are imaginable. Reusable transport, ice mining, oxygen production, buried habitats, solar power, fission, and closed-loop life support. But connecting those pieces into a system that can fail without collapsing is a challenge larger than any rocket. Mars will not become Earth. At least not on the timescale of the first city. Instead, the city becomes a machine that carries a small piece of Earth inside it. Air moving through ducts, water moving through roots, stories moving between generations. And the moment it becomes a civilization will not be the day the millionth passenger arrives. It will be the day a ship from Earth fails to arrive, and the lights stay on.